Okay, this lecture is our initial lecture from Chapter 7 from the textbook. So you'll need to open your textbook to page 206. That's where our first on your own problem is. You need to have your notes printed out in front of you, and you'll need a periodic table to reference. Okay, we won't need a calculator in this lecture. All right, I want you to turn to the very back page of your notes. Okay, so I used to have students write all this out, and then eventually I got tired of that and just decided to type it all up. But part of your chapter has a history of atomic structure. How did we get to the current model of the atom? And I summarized all of this on the back of your notes. Okay, we started with William Crookes, who invented the Crookes tube to demonstrate that gases contain particles. Then a scientist named J.J. Thomson used the Crookes tube to discover negative charges, which ultimately were called electrons, and developed the plum pudding model of the atom. That's on page 209. All right, the Crookes tube is page 201. And then we had a scientist, a physicist named Ernest Rutherford, who did a famous gold foil experiment to discover the atomic nucleus. Okay, and Rutherford developed the first planetary model of the atom on page 210. Okay, so you can follow along in your book and look at the examples in your book. Then Niels Bohr, all right, was a Danish scientist who studied hydrogen and was the first to determine that atoms have these energy levels, that electrons travel around the atom in energy levels. And then the current model of the atom, which has been the model since the 1920s, is called the quantum mechanical model. That goes to page 228. So this covers a lot of pages in the textbook. So in the description box of this lecture, I am going to put a link of a lot of short YouTube videos that I want you to watch about each of these experiments. All right, all these videos add up to less than 10 minutes, okay, of videos to watch. If you will watch those, you should be good to go on what you need to know for the test on the development of the atomic model, okay, from the notes and from those videos. Okay, so again, I will link those videos in the description box, and you can watch those videos on your own time. Okay, if you'll turn over to the front of your notes, let's go through these bullets real quick. So electrical charge, there are two types of charge, positive and negative. A neutral means it has no charge, and what ultimately that means is you have just as many positive as negative charges, and they cancel each other out. Like charges repel, just like a magnet, and opposite charges attract. Okay? And so one of the first videos that I'm going to link called Atomic Structure, watch that video. I would have shown you this in class, okay? So you can watch it on your own, but it talks about the three atomic particles. Electrons, which are negatively charged. We say it has a -1 charge. Electrons rotate about the nucleus. Protons are positively charged. We give that a +1 charge, each proton. They are contained in the nucleus. Neutrons are little bundles of mass that have no charge, also contained in the nucleus with protons. The atomic number is the top number of each element in the periodic table, and it tells you how many protons an atom has. All right, so let's look at your periodic table here. So for magnesium, the atomic number is 12. Magnesium has 12 protons. For cobalt, the atomic number is 27. Cobalt has 27 protons in its nucleus, all right? For nitrogen, 7 protons, all right? So all neutral atoms have the same number of protons as electrons, okay? So that'll give it a neutral charge there. So what I said before, magnesium has 12 protons. It also has 12 electrons. Cobalt has 27 electrons. Nitrogen has 7 electrons, all right? If there's an imbalance and it has fewer or more electrons, we'll discuss that in Chapter 8, what happens. But as of right now, we're just assuming that they are neutral atoms. They have the same number of protons as electrons. So open up your book to page 206, and we will look at 7.1, and you can fill out parts A, B, and C. So part A says, how many protons and electrons are in the following atoms? Okay, so chromium. All right, let's find chromium's number 24. So chromium has 24 protons. So we use a little p, and 24 electrons. And for some reason, electron always gets a little minus there. Okay, if you want to put a plus with proton, you can. A lot of people don't write it that way, but electron gets a minus. So 24 protons and 24 electrons. Let's look at B. We're doing beryllium, right? So beryllium is number 4. So beryllium has 4 protons and 4 electrons. All right, and then part C is lanthanum. All right, lanthanum's all the way down here, number 57. All right, so lanthanum has 57 protons and 57 electrons. As simple as that. All right, let's move on down your notes. Isotopes. So isotopes are atoms that have the same element, atoms of the same element that contain different numbers of neutrons. Okay, so lanthanum's always going to have 57 protons, otherwise it's not lanthanum. However, it could contain a different number of neutrons. Okay, you can have lanthanum that has 57 neutrons. You can have lanthanum that has 54 neutrons or 59 neutrons. Okay, it's still lanthanum, but they have a slightly different weight because they have different numbers of neutrons in the nucleus. So we call those isotopes. A famous one in Paducah is uranium-235 and uranium-238. Okay, so that's 2 different isotopes of uranium. Both of those isotopes of uranium contain 92 protons, right? Uranium's 92. But U-238 has 3 more neutrons than U-235. And what they did at the plant in Paducah for so many years was they separated the U-235 isotopes away from the U-238 because U-235 is fissile, all right, and releases a lot of energy in a nuclear reaction, so they needed more U-235. The mass number is the total number of neutrons and protons in an atom. So mass number, you just add up the protons and the neutrons. So for carbon-12, look at the periodic table and you'll see carbon has 6 protons. Well, it has 6 neutrons because 6 plus 6 is 12. The way you will see it written is carbon-12, just like that, or a little 12 superscript up to the left of the element symbol. All right, isotopes are very difficult to separate because they have similar properties. You can't use a chemical reaction to separate isotopes. You have to use physical means, and that's what they did at the gaseous diffusion plant at USEC for 50 or 60 years. They had to separate those isotopes physically, and it took a lot of energy to do that. All right, let's look at 7.2. All right, so open your chemistry book, turn to page 208. And it says, give the number of protons, electrons, and neutrons that make up the following atoms. So for A, we have argon, and then you have a superscript of 40. So the way you say that is argon 40. To figure out the number of protons, we have to find argon, and it's 18 protons. If it's not 18 protons, it's not argon. All right. Well, we need, how many electrons does it have? Well, it's a neutral atom. You'll be told if it's not. So it has the same number of electrons as protons, so 18 electrons. Now to figure out the number of neutrons for argon 40, you take the number 40 and subtract the number of protons. All right, so that's going to be 22. So we have 22 neutrons. All right, part B, chlorine 37. So this is another way to write it. You can write the entire name out and then the number 37. All right, let's find chlorine on the periodic table. It's 17, so we have 17 protons, 17 electrons, and to get the number of neutrons, you would take 37 minus the number of protons, 17, and that is 20. So 20 neutrons. In part C, we have lanthanum 139. All right, lanthanum we talked about before. We found it on the periodic table number 57. So it has 57 protons, 57 electrons, and then to get the number of neutrons, you take 139 minus the number of protons, 57, so the mass number minus 57. All right, and that is going to be 82. So it has 82 neutrons. All right, it's that easy. Don't miss one like that on the test. Goodness, okay? All right, so I'm going to erase this. If you need to pause the video, go ahead and do that, and I'll be back just a second. Okay, 7.3 on page, so if you'll turn the page in your notes, all right, so we're up at 7.3 at the top of page 2. It says an atom has 34 protons, 34 electrons, 41 neutrons. What's its full name and symbol? Okay, so we need to go find number 34. That's selenium. All right, 34 is selenium. So we know that it's Se. To get the number, we take the number of protons, so that's 34. And then it says the number of neutrons is 41. So that's going to be 75. That is our mass number. Right? That's the number of protons and neutrons. So we just put a 75 in the top left corner, and that is our symbol for selenium 75. You could also write it out if you want as selenium 75 if you wanted. Most people prefer this. All right, so let's finish up the lecture. So we're going to go down to here at this point, and then we'll stop. Okay, so talk about, first of all, it says to read 209 through 213 about the plum pudding model and the Rutherford model. I do recommend that you read this chapter. There's a lot of vocab in the Chapter 7 test, and I'm going to link to the videos about that plum pudding and the Rutherford model. All right, with light, the particle theory of light is that light is made up of photons, which is tiny packets traveling in the same direction. The wave theory of light says that light travels like a wave in the ocean with troughs and crests. Okay, we're going to draw that wave of light right down here in this section in just a minute. The current scientific theory, and it's been this way for about 100 years, is that light has a particle-wave duality. Sometimes light behaves like a particle. Albert Einstein proved this, and we studied this in physics. And sometimes light acts as a wave. All right, so you're going to draw in this section a basic wave diagram. All right, so what I want you to do is draw something like this. In the center, just draw a straight line, center of that open spot. That's the middle of the wave. All right, and then just draw a wave, kind of like that. So from the center of the wave to the top of the wave, all right? So this is called a crest. The bottom is called a trough. All right, right? And the crests repeat every wavelength, all right? So the height from the center of the wave to the crest or the trough is called the amplitude. All right, so A is the amplitude. The distance from crest to crest, or trough to trough, because it's the same, is called the wavelength. All right, we use the Greek gamma for wavelength, okay? I believe that's gamma, I'll double check. All right, and so that's the wavelength. All right, so there's your basic wave diagram, okay? And in your notes it says wavelength, distance between crests or troughs, amplitude, the measure of the height. And then the last thing we want to talk about is frequency. So frequency is the number of wave crests or troughs that pass a given point each second. So in lecture 2, we're going to do some math involving the frequency and the speed of light. Okay, so, but that's where we're going to stop on this lecture. All right, so the homework that goes with this lecture from the book, all right, I'm going to go ahead and erase this diagram. All right, and this, of course, is on my website, but the homework is review questions, page 245. You can do 1 through 7. You might have to read up in the book for some of those, but 1 through 7, we'll get that. And then the practice problems, page 246, you can do 1 through 3. And then, of course, you have the limiting reactant worksheet. Problems number 2 and number 4. Remember, I worked number 1 and 3 for you as examples. So, if you're watching this in 2020, if we come back on Wednesday, this is what will be due. These 10 from the book and those 2 from the worksheet. All right. So that does it for our lecture 1B, and I will talk to you next lecture.